we will go ahead and get started, and within that start, it's going to be a little slow and probably not getting the information you wanted to hear. First things first, I want to make sure this is in the recording and everybody's aware of this. This Unit 1 SPECT quizzes thing is points back for exam 1. Like, do those, and you get points back for exam 1. Okay? I would argue those should be full credit. You should be getting those 100% perfect, right, all the way through. And if you haven't done them, go through and do them. Those are the fundamentals that allow us to advance forward. And if you need more attempts, okay. That's where we start that conversation and you talk to me about it, like, why am I getting things wrong? And I make sure you're good so that you can go through and get those points and prove that you've picked up that content, because that content is relevant for the stuff in the past exam. Okay? To a similar-ish thing, and I'm going to do a wicked scroll here. If we go through and move into Unit 2, we also had these quizzes, things showing up in the modules. Okay? Those were providing practice on the content that was relevant for the exam. Okay? I do think they helped, because I think the exam scores went up significantly. Okay? There are people that did not do them. Do them. There's not a deadline on it. I haven't established any hardcore deadline. There are dates associated with them encouraging you to get them completed during that time, because that's when the content was most relevant. Completing it now is less beneficial because you've already taken exams on that content. So you've kind of lost the utility. You can lose the utility, but keep the points. So keep the points. Right? So if you haven't gone back and done those, you should do them. I'll add that some people may be like, oh, it's only worth a point. What do I care? Okay? If we look within that category is worth, I think, 10 to 15% of your grade. It only has these things in them, which means each of those is worth about a percentage of your grade. Not a point, a percentage. Okay? As we do more quiz things, that point value or that percentage value may go down, but this isn't just a point. These are pretty beefy as far as points go. And since you can get them perfectly correct, you should. Right? That's a pretty big chunk of your grade that you're just foregoing. I want you to be aware of that. After that, we'll talk about the exam more on Wednesday. I think overall the class did much better. I think there were 3 scores that jumped up significantly, which was a good thing. In reading through some kind of secondary things, it sounds like some people appreciated more seeing the context of how and why Unit 1 was useful and what you would do with it. Okay. As a bit of a warning, Unit 3, which is what we're about to go through and start, okay, and Unit 4, in my opinion, gets significantly more challenging. Okay? We're adding more onto it. Unit 1 provided the context of what structure was, so that we can then have a conversation about it. Unit 2 was, how do we organize these things? What things can they go through and do? What are all their actions? Okay? Unit 3 and 4 is now the deeper questions. Why? Why does it do this? Why does it do that? Okay? And so that why question is a significantly harder question. We've slowly kind of been building up to those. Okay? You have to have done fairly well on everything else to then be able to ask that why, because you're going to start looking at pictures and you're like, well, if I don't know what the picture means, you can't answer the question. Okay? So be aware of that going into Unit 3 and Unit 4. Okay? As always hesitant to say things like this because it almost always seems to backfire. If we look historically, the last class that went through and did this, Unit 1 and Unit 2, the exam scores go up, and then Unit 3 dropped like a rock, okay, significantly, okay? It's harder content. It's those why questions, okay? We did push a little bit more time, I think, on the mechanisms and dealing with those why questions earlier on, okay? So hopefully we won't see that happen, okay? But be aware, the content does become more challenging. It's going to require more time to understand and fully manipulate and work through it. Those students that are on that higher end doing better on exam 1 and exam 2 should find the content getting more difficult, but not extremely more difficult. Those people that struggled with exam 1 and 2 may be seeing even more difficulty going up, kind of sharper than you would prefer. Okay? To that end, this is why we have office hours. This is why we have a tutoring center. Get help and push to that content. Okay? Make sure you've got that nailed down. Kind of, sort of? Okay. Again, exam 2, I'll give you more information about exam 2 and the exam after exam 2 grades on Wednesday. I just need a little bit more time to process some stuff. Okay. With that, we should be moving into our next unit. Okay. If we just real quickly flip through the slideshow here, we're looking at 33 slides. I believe almost all of our other slides were closer to 100, okay, within the slide deck. This is a relatively short turnaround on exam time. Okay? We're winding down into the end of the semester. What we're now kind of pushing to is the bane of most students when they talk about organic chemistry, and it's just reaction, 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 reaction. Okay? So we'll talk through some of those whys to help you be able to look at a structure and start to predict things. The flip of that is just, here's a reagent, memorize what it does. Okay? Kind of, sort of? Okay. Questions? No? Okay. If there's no questions from you, I'll ask questions. What's a substitution reaction look like? What has to happen?
It has to be a leaving group.
Okay.
Sigma bond breaks and forms the leaving group.
Okay. So you've thrown out a whole bunch of information there. You had leaving group as kind of a general terminology that we would use to talk about it, but then you also referenced kind of the breaking and forming, okay, of bonds. Can you be more specific about those bonds, or is that all you got? You don't have to be. Just...
You'd say that the bond loses electrons to the leaving group.
Okay, so that breaking of a bond has to do, I don't have enough space to write breaking, so we're just going to call it BRAC. Okay, breaking our leaving group. Okay, those electrons are going with the leaving group. This does become important. Okay, when we use the word leaving, that word leaving implies that that thing is taking the electrons. Always. Okay, that's what it means. Anybody else have any ideas on how you could specify a little bit of clarity with those bonds?
Isn't SN2 sigma specifically?
Okay, so now you're adding a whole, bringing in more language, which is good. Okay, but you said SN2. Okay, what is SN2? Do you have more?
Form substitution, isn't it?
Okay, does anybody know what SN2 is in reference to?
Concern.
Okay, we're throwing out awesome words that describe what it is. Yeah, SN2 is a concerted mechanism, simultaneous. I actually said the answer, damn it. It's a mechanism. I didn't ask for the mechanism yet. Okay, what we're trying to identify is all those pieces that go with it. So you're right, identifying the mechanism does become important. We do have SN2, okay? But you also added an important bond or an important reference back to the bonds. You said SN2 and then you followed it with sigma. The bonds that you're breaking in a substitution have to be a sigma bond. The bonds that are breaking and making in substitution will always be a sigma bond. Okay? So we have SN2 as a mechanism. Okay, so now what you're starting to look at is the how. I would argue we haven't even finished the what. Okay, we're breaking a bond, we're forming a bond. You mentioned breaking is the leaving group. What's the forming? Okay, we can switch it up. What's the leaving group leaving from?
Substrate.
Right, the substrate. So if we're trying to address kind of all of these pieces, the leaving group leaves from our substrate. What causes the leaving group to leave?
The nucleophile.
Right, we don't even have to set it up. About to go all hangman on you. That's our nucleophile. Okay, what is a nucleophile?
Ones that donate electrons.
It's the thing that donates electrons. Okay, which is fantastic. Okay, on the exam, everybody nailed that. Great. Okay, so we know those definitions. We now have to start working through applying those things out. So we've got a nucleophile, we've got a leaving group, we've got a substrate, we've got breaking, we've got forming. How does it break and form? Okay, or potentially, more importantly, when does it break and form? Okay, well, in the SN2, as you guys were referencing, it's concerted. Okay, or simultaneous. What does that mean? All of that stuff happens at the exact same instant. Okay? How else could this happen? Could all happen at once or in steps. Okay? In separate steps. Okay? And if we're going to move into separate steps, we would call that mechanism SN1. SN1 is a bit weird because it's not an elementary mechanistic step. Okay? It's the grouping of elementary mechanistic steps that we then call SN1. Okay? Why do we want to reference it as this fancy thing? Because it's a special category of the substitution reaction. That makes sense. So what are the mechanistic steps that go into SN1? Okay, I'll cheat and say the easy answer. Well, we're going to break a bond and we're going to make a bond. For those of you being like, but isn't that what substitution is? Yeah, that's why we call it SN1, because it's referencing substitution. Those are the two things that need to happen. Do we have names for those two things other than breaking and forming sigma bonds? Yes, yes we do. What are those things called? Elimination is unfortunately not a mechanism, that's a reaction. Okay? And eliminations are different from substitutions because what happens in an elimination? Form a pi bond. Substitution's all about sigma, which means if we're asking what are the mechanistic steps in an SN1, it cannot be elimination because that's involving pi bonds.
Is it not still breaking sigma and making it's the same thing but happening?
What's the name? Okay, because that becomes the next thing, is you have to deal with multiple choice, which means you have to talk in the language of the class. If you can't talk in the language of the class, it's very hard to make that communication, and that becomes a bigger challenge. This is why those words are given to you with those definitions so that you can pick up what they are.
So rationalization.
Okay. Complications of these individual mechanisms, we will have to worry about whether we have multiple products or not. And this is where we can encounter the term racemization. I have no idea how to spell that. Racemization, racemic, racemate. All of those things are referencing the same content. Okay? Have we talked about that word before? No. Okay? Because that's new content. We haven't talked about the complications of any of these. At this point, all we're trying to do is summarize what we should already know. Okay? And using the exact language isn't super critical, except that it does tend to show up on exams. And if you don't know the language, that becomes hard to answer questions. So if we talk about breaking a bond, what might we do? What happens if we cut open a cell? We've done some biology stuff, right? What do they call that if something cuts open a cell? I'm hoping. What's that?
Dissect or
That's cutting open an organism, but if the
histology?
lysis, there we go. Okay, lysis is talking about cutting open things.
I thought heterolysis.
Heterolysis. Okay, we talk about it as heterolysis because the electrons in the bond go only to one atom. So one atom is negative, one atom is positive. They're opposites, which is kind of where the hetero is coming in. I'm sure if I knew my Greek prefixes better, I could explain that better, but that's the best I got. Okay, lysis is our cut. So we're talking about heterolysis. Okay, and what else? Heterolysis is breaking the bond. How do I form the bond?
Coordination.
Okay. Those are the big key aspects, okay, kind of terms that come out of substitution that you should already know. How and why and when and all of the complications that come with those is what this unit is. Okay? We did substitution. What does that mean we need to do next? Okay, we know one thing in the elimination, we need to form a pi bond. Is that it? Oops. I'm going to attempt to color code. We're going to lose 2 sigma bonds. Okay? In the overall reaction, that's what's going to happen. Okay? What sigma bonds are we going to lose? I'm going to throw Kimball under the bus just because you know the answer. You may not acknowledge it, but you've already said the answer. You want a little hint?
Yeah.
One of those sigma bonds is the leaving group. You need to break the leaving group. Okay. What else needs to happen? Now it gets harder.
Electrons need to be donated? No, that doesn't matter probably.
Becomes hard. So one of the things that might be challenging is you're trying to use language, okay, in a language that you don't know because it's organic chemistry and you haven't worked in organic chemistry before. Okay? We're also just barely using language that you just studied. Theoretically, you've studied a little bit more the structures. So do you think it would be helpful if we shifted away from using the language and shifted instead to a structure? Yeah? Okay. So let's just start it with this. I'm just going to do a single atom. There's my bond to a leaving group. If I'm going to make a product, can I make a double bond? If I must break that bond to the leaving group. Why not?
There's no other electrons? Or
What's that?
There's no other bonds, but that doesn't seem,
I would need you to elaborate, I think. 'Cause, I mean, technically we have hydrogens out there.
okay, never mind.
Where's the pi bond form?
you can't because the hydrogens.
Ah, there we go. We go back to our structure. Okay, for a pi bond to form, it needs to form between something, okay, and something else. But those somethings cannot be hydrogen because
Only can hold 2 electrons.
hydrogen can only have 2 electrons. Which means if this was the structure I was looking at, this isn't going to work for an elimination. Okay, so what we could try and go through and do is we could draw another carbon. And if I was going to try and draw the product of this, where would the double bond need to be?
Between the carbon and the
Sweet.
other atom that is.
Right?
Or another carbon, I guess.
Right? So I've formed a pi bond. I broke a sigma bond, the leaving group. But I'm supposed to break 2 sigma bonds. Why do I have to break 2 sigma bonds?
Well, the name is elimination, so that just like.
And I count 1, elimination, 3, 4, 5.
Well, would it just not eliminate the original molecule, I guess? No.
And so that becomes a misleading thing as we start to use the language as we would like to use it in the natural world. Okay? And chemistry changes things. Okay? So we have to be careful to use the language in terms of the chemistry context. Right? Broke the leaving group and I formed a pi bond. Okay? We said we had to lose 2 sigma bonds. Why did I need to lose 2 sigma bonds? Can't I draw this? Is there something wrong with what's in the green box?
Carbon.
I've exceeded the octet of that carbon. Okay, which means what must also happen?
Hydrogen is broken. The bond
The bond between the carbon and the hydrogen is also broken. So not only do I have to break the leaving group, but I also have to break a carbon-hydrogen bond. Do I break it in the same fashion? Okay. What did we say the leaving group did? The electrons went with it. If the electrons go with it, what happens to that carbon?
loses lost electron.
It loses electrons, which means its charge would be positive. Cool. Where do I get the electrons to make that pi bond? To make that pi bond, I need more electrons. Where do I get those electrons from? What else do we know must happen? We've already specified it. It's in our list right above.
Break a
Break a what?
CH group.
I have to break that CH group. The electrons in that bond. Okay? If we look at the leaving group bond, the electrons went with the leaving group. Why? That's the definition of a leaving group. Is the definition of hydrogen that it takes electrons? Is the definition that it leaves electrons? Does hydrogen have a definition? No, it doesn't. So what should happen to those green electrons? Should they go with the hydrogen or should they go with the carbon?
With the carbon.
Why should they go with the carbon? Ah, okay. So cool. We can start to push and look at the properties of those individual elements, carbon versus hydrogen. Carbon is slightly, very slightly, more electronegative than the hydrogen. So if you were forced to make a choice, you're kind of being forced to make a choice, you would expect the electrons to go with the carbon. Okay? But you should be able to make a better choice than that, or a better explanation for why the electrons need to go with that carbon.
To satisfy the octet.
The red one doesn't have its octet satisfied. So it's not that you're necessarily wrong, but it's an irrelevant point, unfortunately.
It's just that the carbon's the only one that can hold it, right?
So now you're making the argument that carbon is better at holding the electrons than hydrogen.
Yeah.
Okay. Why?
Because of the hydrogen just can't. They can only
Why?
do-
It would have to. What did you say was the most important thing that we should be doing in this particular reaction? What are we trying to do?
Does it have to do with resonance too?
Maybe
Form a pi bond.
form a pi bond, because we said elimination was the formation of a pi bond. Right? And if I took those electrons and drew them in there, right, that would say I moved the electrons from one atom to a bond. That would be another way of saying that I've done resonance. So there you go, good call out. And I've formed a pi bond. What is the relationship between those two structures? Yeah, they're resonance. They're one and the same. Which means when I go back to that bond breaking, why do I know the electrons need to go with the carbon? The whole point of this wasn't just some arbitrary random question we thought of. We said, I want to know what an elimination is. So I'm going to start going through all of the pieces that I know of elimination and draw the structures. Use the structures to help guide me to the definition of what it is. Right? We said we had to break the leaving group. Yes. But just breaking the leaving group wouldn't give me the ability to make a double bond, because a double bond requires something more than hydrogens. So I drew on another carbon. Right? It could leave, then I got a positive charge. Right? And making the pi bond, I also have to remove a hydrogen. The structures tell me that. I'm using that information that we learned in Unit 1. Octets can't be exceeded. That's a problem. I use that to leverage and say I have to break the hydrogen. Now the question becomes, how do I break the hydrogen? Well, what information do I know? I know I want to make a pi bond. Why do I know I want to make a pi bond?
Because elimination.
I started this trying to figure out what elimination was. So if I'm going to do elimination, I better make a pi bond. Whether I did a good job or a bad job is irrelevant. What I'm trying to do is nail down the bare bones of what that elimination means. Once I have that, I can now start to say, is it good or bad? Okay, but if you have nothing, you need something, draw it. Draw it so that you can hang some information and meaning on it. Right? To make the pi bond, where do those electrons in that carbon hydrogen have to go? They have to go to make the pi bond. Because if the electrons went with the hydrogen, do I have any electrons to make the pi bond? No, I wouldn't. So I wouldn't be able to do an elimination. Which therefore means when the hydrogen breaks, the hydrogen leaves the electrons. Right? They are left behind with the rest of the structure. The leaving group leaves with electrons. 4 little letters made such a big difference. Who knew? Huh. Just driving Phoenix. No. Whatever. Okay? You can think about that one later. Maybe when you're driving home. Okay? So cool. We even added drawings into this. Okay? We break the leaving group, we break the carbon hydrogen, and we need to form the pi bond. Interesting observation. We break the leaving group and we break the hydrogen. Did I actually make the pi bond in this red structure in that corner? Do you see a pi bond? No. We only see the pi bond when we draw the resonance. Which means, how critical is the formation of the pi bond? That's pretty meaningless. If I understand how to break the leaving group and the hydrogen off, the formation of the pi bond becomes a natural result, which is really weird because when we think about elimination, what's the first thought that comes to mind? Form the pi bond. Because structurally, that's what we see. Electronically, it was pretty irrelevant. Okay? That's what we're trying to do, is break down what those structures mean. Use some of that language and leverage that to try and pick up more information and more information and more information. Okay? What more information could we bring in? Okay, well, we just talked about all those things that had to happen, and we drew them out stepwise so that we could see them. Does that mean it had to happen stepwise? No. Okay? When you go through and figure out your plan for your academic, oh, I'm going to take this class and this class and this class, what happens when you fail a class? Does that mean you stop everything and go back to that one class? No, you continue with the path, and then you also go back. You do both simultaneously. Okay? So we're looking at this work as a work in progress. What we now have to go back and decide is, does it need to all happen this way? Does it have to? Or are there other ways to go through and do it? Well, that's the how. That's the mechanism. Are there different mechanisms for elimination like there are for substitution? Right? And that might be a hard question, but that was the point of the last unit, was to give us some rule sets on what we could fall back to. Admittedly, SN1 was not one of those rule sets. SN1 was not talked about in the last unit. It was talked about in one of our labs. Okay? So should we put someone on the spot? I've already yelled at Kimball, so we might as well push somebody else. You said SN1, Crystal. Why did you say SN1? Because I didn't tell you that.
Just because I remembered that's, even in lab, when we did both reactions, one was above the other.
Okay. So in lab, we had an SN1, okay, a description. Okay. So do we have different eliminations? Cool. We could reference electrophile elimination and nucleophile elimination. Awesome. Are there other eliminations? E2. That E in E2 was elimination. Right? So there's nucleophile eliminations and electrophile eliminations. Okay? Those are in reference to what's happening when you formed the pi bond. What was eliminated from the structure when the pi bond was formed? So if we go through and look at our mechanism, where do you see the pi bond forming? Is it up here? No. Okay. Is it down here? I think it's a little bit harder. Is it here? Yeah, this is the formation process. This is how the pi bond was made. So we could say yes here. Okay? To do this, we had to have these electrons come in to make that pi bond. Yeah? Where did we get those electrons from? Well, to figure that out, we could go backwards. Where did we get the electrons from? From the bond between the hydrogen and the carbon. Those electrons, if we wanted to get a little bit more specific, did that, which means what else is floating around? The hydrogen. With what charge? With a positive charge, because it's missing its electrons. It gave them up to the carbon. Is that atom more a nucleophile or an electrophile? So what kind of elimination did we do here? An electrophile elimination. Okay. What's the E2? The E2 is all of that stuff happens at once. That sounds kind of familiar. That sounds kind of like what happened with the substitution. And when it happened all at once for the substitution, what did we call it? SN2. That 2 was in reference to it effectively all happening at the same time. So if we do all of this elimination, breaking and forming and breaking at once, that would be an E2. If we break it into steps, we're going to encounter an electrophile elimination, but that electrophile elimination is what's happening down here. What happened here in the previous step? What changed in that little box? I know it's not little. That green box, what changed? Yeah. What mechanism does a single sigma bond break? Heterolysis. Okay. And this might start to sound a little bit familiar. That sounds an awful lot like substitution, particularly our SN1. Guess what one of our major complications are of our substitution and elimination reactions? They compete. So if I mix together the reagents that would allow me to do a substitution reaction, I have to be real careful, because not only is the substitution reaction going to run, the elimination will also run. So what I need to do is understand the differences between substitution and elimination so that I can help push one of those reactions happening over the other. This means I have to have a pretty deep understanding of what all of those intricate little pieces are and what's going to help navigate all of those little systems. Kind of, sort of? Can I clear a lot of that away? And by a lot, I mean all of it. And actually, I honestly don't remember how far my slides jumped right away. Oops. Let's see what the slide jumps to. That's good enough. This summarizes some stuff. So we need the language now to be able to talk about this. We started to talk about some of these patterns. Okay, we mentioned a substrate. That substrate contains the leaving group. What reacted with the substrate when we looked at a substitution? You're like, why'd you delete everything? It had the answer up. I know it did.
Sorry, say that one more time.
What reacted with the substrate in a substitution? The nucleophile. And I'm going to leave a nasty space here. We'll come back to it. How do I ensure that the substrate and the nucleophile can talk to each other? I have a solvent. Okay. One piece in the elimination I goofed on. Okay. So what I'm going to do is we'll kind of bring it back with the structure shown here. So we break our leaving group, right? Then what happened in our next step? This reaction is a little more balanced, so it's a little bit easier to see what happened.
Electrons move to the right.
How? So what you just told me sounded like I should be showing arrows, but I don't know where to draw those arrows.
From the sigma bond to the carbon.
Which sigma bond?
The one connected to the leaving group.
Leaving group's not there. Sounds like you're talking about that.
maybe.
Okay. What do arrows show the motion of?
Electrons?
How many electrons are on a positive charge? Damn.
I just read it.
Yeah, we could draw an arrow. Okay? I would argue it's hard to draw an arrow because you don't know where the electrons are. Okay? So what else changed when you look at that last step? So we can ignore the rest of the world. It all disappears. How many carbons do you see? How many hydrogens do you see? Okay? I see what your mouth is doing. You're counting too hard. How many hydrogens do you see? Okay, you're not wrong. I understand what you were doing, but I didn't want that. You only see one. Where the heck did that hydrogen come from?
Which one? You said red one?
Because presumably Crystal's saying I see a hydrogen.
Oh, I
Right? Is that what you're saying? Where did that hydrogen come from?
the silver? And the nuclear?
It's like the example we just had. I don't know how to word it.
Okay? And this becomes one of the big challenges with eliminations, is we don't see hydrogens. You remember back in Unit 1 where we had silly test questions, which how many hydrogens are in this molecule? Okay? And we get all the questions wrong because we forgot about all the implied hydrogens. Yeah, I remember that. Students hate that question. They're like, that's so stupid. Why would you ever do that to me? Because you do it to yourself when we get to this question. How many hydrogens on that first carbon? How many hydrogens on that next carbon? We're going to call that a purple carbon. 2. How many hydrogens on the green carbon?
3.
How many hydrogens on that same red carbon? Come on, pen.
3.
How many hydrogens on that same green carbon? How many hydrogens on that purple carbon?
1.
What was that?
2. 1.
I mean, shouldn't it be 2? Why should it not be 2?
The octave.
Where did that red hydrogen come from? That big old red circle. Perhaps if we color code it a little differently, that H plus is that purple hydrogen from the very beginning. And if we were a little bit more specific, if we now add that there, that hydrogen should not have any electrons because it needs to become H plus, which means what happens to the electrons? Do they go towards the hydrogen or away? Away. Where away should they go? There's the formation of our pi bond. We're now breaking a carbon-hydrogen bond. So you ready for the next fun question? Clean some of this up. Okay. That molecule acted as what? Switch up the question. There are 4 things it could have acted as. What are the 4 things? That's a mechanism. That's the beginning to end of in fact, actually what you said was just a reaction. It could be a nucleophile or an electrophile
Or an acid or a base.
or an acid or a base. Cool. Which is it? Why is it an acid?
Donates electrons.
Did it donate electrons?
It's
Donates
the H plus.
It donated H+. What did it act as? It acted as an acid. How easy was it to break that carbon-hydrogen bond? That was pretty easy. So you saw that right away. Okay. So how easy was it to break that carbon-hydrogen bond? That was really challenging for you to go through and see. But if I went through and I drew an OH bond, would you have been okay breaking that hydrogen off? Yeah? Why?
That's what we've been dealing with, obviously, with an acid-base reaction.
Or how about HCl? Would you be okay breaking that hydrogen off? Yeah, why? Okay, and you got the right idea. It's what we've been dealing with. Okay, it's what we've been dealing with when we look at acid-base reactions. Okay, and what we're talking about with those is we ranked their ability to donate hydrogens. And that ability was dictated based off of what? Why was HCl able to donate that hydrogen? So regret how I went through and did this.
Because it has the electrons to do stuff.
All structures have electrons, so I'm not quite sure I understand that. Why is HCl able to donate H+?
Because it
This is an acid.
But why? Why can it act as an acid?
It's orange.
We look at the stability of the conjugate base. When we look at this species, we go through and say chloride is very large and it can stabilize that negative charge well. Because it stabilizes that charge well, we would predict lots of H+ to float around because I can make chloride stable on its own. Would I expect that to be the case with a carbon-hydrogen bond? Why not?
It's not very electronegative.
If we now again look at the stability of the conjugate base, that carbon cannot stabilize the charge very well. We're looking at a small atom with low electronegativity, no resonance, no induction. That would suggest it should never act as an acid, and yet what is it doing? So what could we do to help it act as an acid? Because we know the elimination reaction needs to work this way, but it doesn't want to act as an acid. How can I make it act like an acid? How? We know it needs to happen, but it doesn't want to. If I asked you for $100, would you be willing to do it? Okay. What if I'm holding a gun to your head? Oh, wow, that changed fast. Okay. For the record, I'm not holding a gun to the head for the recording. Everybody understand that? There's no guns at all involved in the room. Okay. You can make something act like it if you provide the right incentive. What's the right incentive to make a molecule act like an acid?
Give it electrons.
From what? It doesn't want to donate H+. So what should you do? What do acids react with? So what should you add? So to do an elimination reaction, what's one of our common components? It starts as an acid. To make it react as an acid, we need to add a base. So if we're now breaking down all of the components, and this is where I'm going to regret backtracking out of all of this. Yeah, this is pretty painful. I shouldn't have done it this way. Wish I knew how to do this faster. Oh, Lord, man, it's still going. Where's my summary? It's probably faster just to rewrite the summary. There it is. Yeah. I said I left this big awkward space. What's in that big awkward space? So when we're talking about our substitution versus our elimination reactions, these are the pieces that we need to be addressing and thinking about. I need to know what the substrate is. I need to know what the leaving group is. I need to know what the nucleophile is. I need to know what the base is. I need to know what the solvent is. Those pieces dictate whether I'm doing a substitution or elimination reaction. And they will dictate how I do the elimination reaction or substitution reaction. Because not only am I trying to differentiate substitution versus elimination, I'm also trying to differentiate SN1 versus SN2. I'm also trying to differentiate E1 versus E2. To do that differentiation, I have to know what those terms are and what they mean to the overall reaction. Okay? That's why in the last unit, what did we talk about? Solvents, bases, nucleophiles, and leaving groups. All of those components were directly addressed so that you had that language that we could now move forward. The substrate is kind of a new one, but ultimately all the substrate is the thing that's getting acted on. It isn't that big of a deal. Okay? So when we go through and look at these reactions, what we're trying to decide is what mechanism is happening or what reaction is happening, and then what mechanism. So if we look at that first arrow, that top arrow, what reaction is happening? Okay. Selective vision should jump in. That's what I'm asking about. What is the overall reaction that has happened? And if we push selective vision even further, is substitution. So this would be NS. Okay? What happens in the next one? And if you're asking yourself, that looks like the same thing, it is. That would also be a substitution. But for me to differentiate which substitution or what type of substitution is happening, I would have to understand something about the mechanism. I would have to understand, is it happening all at once or is it happening stepwise? Well, you tell me.
First one, stepwise, second one.
And when we talk about stepwise, what mechanism are we going to call it? SN1. Okay? And that one, full disclosure, is a hard one because we haven't officially said that yet as far as the lecture goes. As far as lab goes, we've done it. The next one where it happens all at once, we call it SN2. Okay? That's that mechanistic step. SN1 becomes a hard one because the SN1 is the overall picture of how that happened. So if we push in the overall picture, it happens by doing a heterolysis followed by a coordination. Okay? Note, in the substitution, what was important? The nucleophile or the base? What was important in our substitution reaction? A nucleophile or a base? Nucleophile, and we know that because it says it, yes. You just don't make things more difficult than they have to be. It says it. Nucleophile is relevant for our SN reactions. Okay? What happens in the next reaction? This is now an elimination. How do you know it's an elimination? You form the pi bond. Awesome. We just said the formation of the pi bond wasn't a big deal, okay? But it's a huge thing for us to hang that it's an elimination reaction on. Once we know it's an elimination reaction, we can take a step back and look at the hows and the whys. But first, we have to acknowledge what changed. What happens in the last one? Also an elimination reaction. Okay? How do I know the difference between those two elimination reactions? The number of steps involved. So I would go through and name them differently to account for that. What do I name them? E2 for which one? Good. I don't think it's shown as a subscript. I think it's a capital. And the bottom one is E1. The E1 also breaks down, similar to the SN1, into different mechanistic steps. The first step is a heterolysis. The second step is our electrophile elimination. Both those words are way too long for me to write all the way out. Is that okay? Thank you. And right? If we now look at those summaries, hopefully we notice some issues. If I have, or some good things, if I have an E2, does it look like the E2 competes with anything? Does the E2 do the same thing as anything else? I know, my questions get kind of hard and vague. I would actually accept yes and no as valid answers to this question. So let's try that again. Does the E2 compete with anything? What's that? Sure is not yes or no, but I'll accept that as a yes. Okay, what is it competing with? E1, it's producing the same product. So you're recognizing similarities in those reactions. Okay, those overall reactions. Except, what does the E1 do differently? Multiple steps. So while the end product is the same, how you do it is different. What does that mean for us? If I can figure out how it's done, I can prevent that first step, which means there is no competition, and E2 runs on its own. How about the SN1? Does the SN1 compete with anything?
Yes.
Yeah, the SN1 should be screaming competition because it matches the E1. They both do the very same thing right out of the gate. The difference comes in the next step. They either coordinate or they electrophile eliminate. What's the difference between that coordination and the electrophile elimination? Yeah, but why?
Because they're different mechanisms.
They have their exact same starting material-ish. That ish is a hint. How is the SN1 and the E1 different? That's only once we get to the products. But I don't have products yet. So what differentiates coordination versus the electrophile elimination? If I don't have the products to help me dictate that difference, what do I need to look for?
The bond.
Okay, we could look at the bond. What bond? Should I look at this bond? I would say it rhymes with show would be your answer to that. No, okay, good. What bond should I look at? Okay, we could look at that hydrogen bond breaking. Is that an easy bond to break? No, what had to happen? We had to show the hydrogen, but That helps us see that the hydrogen is there, but that's still not an easy bond to break. How did we make that bond break? Yeah, we take the hydrogen off. What thing would take the hydrogen off? Cruel, horrible thing would remove a hydrogen from a structure. What cruel, horrible thing would accept a hydrogen from a molecule? So in the elimination, I need a base. What's happening up here? What's happening in the substitution? What do I need to cause the substitution, or SN1, to happen? I thought I heard you say something else. I was like, yeah. Leaving group's already gone. What is the difference between those two boxes? What is the thing that is missing? I think you just said it. Yeah. You need a nucleophile. So in the substitution, I need a nucleophile. In the elimination, I need a base. So all I have to be able to do to differentiate whether I'm doing substitution versus elimination for the SN1 versus the SN2 is be able to differentiate a nucleophile from a base. What does a nucleophile do? Yeah, that's a good start. Lovely. Donates electrons. I love it. What does a base do?
Receives, right? Hydrogen.
Okay, cool. So that's obvious. Hydroxide. Nucleophile or a base? Why is it a base? Oh, that's interesting. You said it was a base because it donates electrons? Didn't we say that donates electrons was the nucleophile? The base was accept a proton. How does a base accept a proton? What must it do? It would have to have a negative charge. What does a nucleophile need to do? Donate electrons, which means it would often have a negative charge. What's the problem with differentiating bases and nucleophiles? Yeah, it's really hard. They have effectively the exact same definition. The only way we know whether it's acting as a base or a nucleophile right now is to do a reaction to see which it did. That's a pretty piss poor way to go through and define it. That's why we need to drill into the definitions of nucleophiles and bases to understand the core functional difference between them. That's one of the videos that you're supposed to watch that addresses that difference. Is it easy? Hell no. Okay. But there's subtle clues that you can key in on to try and pick off on it. Hydroxide is an unfortunate one, which is why I picked it. Guess what hydroxide can do? Both. Yeah. It can act as both a nucleophile and as a base, depending on the circumstances it's in. What does that mean if we're going to try and make or force an elimination or a substitution reaction? Don't pick hydroxide because it's going to do both things. So what we're trying again to do is look at those pieces and shuffle through the very critical nuances of what makes each of them different, allowing us to predict one path versus another. Okay? We had big picture stuff for the whole rest of the semester, whole beginning of the semester. You're now into the weeds of trying to define what's happening in each of these cases. We've got an energy diagram written in the upper right-hand corner, so we could go through and use that to help us out. Okay. What reaction do you think I ran?
SN2,
Why SN2?
because we just see one transition state.
One hump, right? One hump is one transition. That one hump means one reaction. Awesome. I like it. Okay. Sorry, I changed my drawing a little bit. Does that have one hump?
Yes,
Is this one also SN2? And now everybody's like, we were real fast with that first one, but now I don't know. Yeah, no, this one shouldn't be an SN2. What is this one? Why is it E2? Why did it all of a sudden change to E2? What was the difference between this one and the first one we drew? Should we put them both up there? Yeah. You saying yes just so that you have a little longer to answer?
I could probably SN2 begin with the higher energy and end with lower, and then E2 begin with low energy and then end with the
Cool, so you're looking at the difference between those two diagrams. I love it. Why is the E2 higher in energy? Just that last little bit.
because it ends at that high.
But why? Why is it ending at a higher energy? What is it about? Does it?
No.
Right? And so I understand where you're going with that. You're like, but it has a charge. Well, one of the things that I didn't balance out here was the leaving group here typically has a negative charge also. So all we're looking at now is our, oops, I meant to erase. They both have charge. Why should the E2 be up and the SN2 be down?
Positive to give? No. No, that's the opposite.
Wrong focal point.
Okay.
Okay, looking at the charge is a good idea, but ultimately the charge isn't what's going to differentiate you here.
Is it because the double bond and they're like, what?
Oh, can you cross it? You're right there. Okay, so we'll push that a little bit louder in case no one could hear her. She's saying, is it with the double bond and then some hand gestures, which
You get, but you don't.
I get, but I can't accept it until I get some more, either better hand gestures or more words to go with it.
They
What do you guys
can't
think?
Move around. They're not imposable.
Okay, that's interesting. The pi bond can't rotate around. Is that really going to change the energy, though? I mean, a little bit, but that's going to be pretty subtle. Why can't it rotate around?
Because it's not, should I say it's superimposable or not imposable?
I think you're
I just
using
know
those
'cause
words
the
incorrectly. I
molecule
really
models.
like your hand gestures,
Yeah.
but I don't think your words mean what you think they mean, and so
Yeah.
I think there's a translation issue that's missing. Okay? You're saying stronger. What's stronger? Is the pi bond stronger than the sigma bond?
Yes. Well, no.
No.
I don't know.
So, because you didn't mention pi, did you?
No, I just said,
Ah, okay. So pi is an awesome piece to add to this. Because yes, it has to do with the pi bond.
well, molecule model kit, I just remember you showing us trying to twist a pi bond compared to a
Yeah.
sigma bond.
And when we try and twist that pi bond, the p orbitals no longer overlap, right? Which is why you can't twist, because you'd be breaking the pi bond. Okay? But what does that mean about the pi bond? Yeah? Okay? Which goes also back to the strength of the individual bonds. The sigma bond is a stronger bond because it's a direct overlap of orbitals. The pi bond is an indirect overlap of orbitals, not as strong. Because it is not as strong, it is a higher energy. So the instant I make a pi bond, what have I moved to? A higher energy. So when we look at the elimination, the pi bond is a higher energy than the starting material. That's why we're seeing it go up in energy. For the substitution, we're seeing it go down in energy because we're making a more favorable bond. The pi bond is never more favorable as far as our structure goes because it's a higher order bond. Okay? To your superimposable, that's what I think you were kind of referencing with the p orbitals rotating and not technically a different system. Okay? But what that's explaining is that our p orbitals are higher in energy. If they're higher in energy, that's why the product is higher in energy. So I can look at those two energy diagrams and I can say one is SN1 and SN2 and one is E2 because they're single humps, so they're the two-type mechanism, right? And then where the product energy is relative to the reactant tells me whether I'm doing substitution or elimination. What does that mean back to our SN1 and SN2? How would I draw the SN1? Two humps like that?
No.
How do I fix it? How do I draw the E2?
Same, but the beginning level starts low.
And then it's hard to nail down exactly where your product, actually, it should be lower than the intermediate when we get our E2. Sorry, what are we talking about? E1. So we're now pulling at that information that we knew about our energy diagrams to dictate what's happening within our individual structures, how many different humps we're seeing, where those intermediates appear, what's happening within those. If I want to talk about changing the speed of this, or increasing the likelihood that I get an elimination reaction, what might I want to change about my energy diagram? Say, what happens if I did this? Would I expect that product, that purple spot, to be a better product than the red product? We're in the upper right-hand corner looking at our energy diagram. Is that purple one a better product than our red product?
Yes.
Yeah. Could I get different stability pi bonds? Yeah, in fact, we've talked about that. We look at our pi bonds have varying stabilities. The more substituted the pi bond, the lower the energy. So if I have a substrate, starting material, that results in a more substituted product, I would expect a larger percentage of that E1 reaction to happen, or that elimination reaction to happen. Okay? So now it's how do I change the substrate to ensure that happens? So what we start, again, needling at is, well, how do I change? If this changes, if that energy changes, what does that mean? How do I draw that representation? Okay, so for that E1, we could go through and say, well, here's just a pi bond like this with hydrogens all the way around versus a pi bond with carbons all the way around. What would that backtrack through? Well, for the E1, we would need a carbocation. Right? And then we backtrack that to our starting material with a leaving group. What's a good leaving group? Something that's willing to take the electrons and be stable. All of our halides are great leaving groups. Can I classify those two starting materials? They're both alkyl halides, right? But in one of them, the chlorine is connected to a carbon that is connected to only one other carbon. In the other, the chlorine is connected to a carbon that's connected to 3 other carbons. Do we have a classification system that allows us to differentiate those? Yeah. Connected to one other carbon, it's called primary. Connected to 3 carbons, considered tertiary. So what does that suggest for us? Well, the E1, I would expect the tertiary to produce a more stable product, so it's going to react faster than the primary. And what I just answered a question about was the substrate. So I could look at my starting material and be like, boom, that's going to do E1. That's pretty awesome. A quick superficial view of your starting material with this underpinning allows you to backtrack all of that knowledge. That's pretty wicked. Okay, but what you've got to go through and process is how is that different for all of our reactions. Okay, and we'll come back to that in a second. Okay, and what we will end up seeing, okay, and go through is these summaries. For an SN1, what do you want for the substrate? You want a stable carbocation, leaving group, nucleophile, solvent. Okay, and bottom for the black, we get some complications. Those are high-end level questions that you'll probably see 1 or 2 on the test would be my guess. SN2, exact same issue. What you've got to go through and do is process what it means for each of those things and then find that information. Okay, you can see it summarized into a table, SN1 versus SN2. Okay, you do the exact, whoops, go fast, because I want, go faster. Oh. We do the exact same thing for elimination. Okay, E1 and E2. You could look at the summary there. We could then put it all together and say, if I'm going to look at E1, E2, SN1, SN2, look at all of those individual pieces and then decide, what does that mean? Is this a good thing for this mechanism or a bad thing? And so what you're now trying to needle your way through is each of those pieces. What makes a nucleophile? What makes a base? What makes a good substrate? What do those individual mechanisms want to allow them to occur? That's looking at the stability of each and every single structure you draw. What if you don't draw structures? You're going to have to memorize it. You're going to have to memorize it right out of the gate. Okay? Your odds of success, if you refuse to draw, are slim to none. Okay? Please start drawing out your structures and start evaluating all of those nitpicky details behind them. It is challenging, but that's where we're at within the semester. Okay? When we talk through those substrates real quickly all the way up the beginning. Nope. Ta-da! All of these functional groups have the ability to do substitution or elimination in some fashion or another. Okay? And we could run through it and say, this is what an alkyl halide does, this is what an alcohol does, this is what an amine does, this is what an ether does, this is what an alkene and alkyne do. Okay? And ultimately what we end up doing is saying the exact same things over and over and over again. Or we just acknowledge that they all have a common pattern, and we have to find how that common pattern relates to each of those functional groups. That's where this gets neat, and where I think it gets fun. It requires practice to look at those pieces. Start doing that practice.